Okay, so good morning to everybody. So today, for the colloquium, we have the pleasure and the privilege, I would say, to have a renowned international scientist in the field of cosmology, which is Professor Luca Amendola from the Institut für Theoretische Physik in Heidelberg. He is the leader of the cosmology group there, and he is well known for his contributions to the field. If you are in the field, of course, you know this. It's impossible that you don't know this fact, and probably you have the book that he wrote together with Shinji Sujikawa about dark energy, which is a book from Cambridge University Press. It is a well-known book. I mean, it is almost impossible to work in the field without having, this consultation book. So, of course, he is a real expert on the subject of dark energy and many other aspects of cosmology, of course. So, I just want to say that it is, as I said before, that it is a great privilege. We tried to bring him here few years ago, but it was impossible. So now it became possible. So we are very happy to have you here. So Professor Amendola is going to talk about cosmology without assuming cosmology. I mean, in these days where cosmology has some tensions and discrepancies and kind of crisis, let us say, in the field. So perhaps this model-independent approach to cosmology can be very fruitful. So please, Luca, thank you very much for coming. So we are just hearing you.
Thanks. All right, so thanks a lot. Thanks a lot for the invitation. As Jean said, I tried to come, but I was not successful in the past few years. And now finally we started all traveling again. So I took the first chance to visit Barcelona again. It's a great pleasure to be here. Thanks again for the invitation. I will not mention the word dark energy at all in my talk. And let's see if that's true. That's my commitment. Let's see if I succeed. Probably will not. But anyway, so I will talk about something related, of course, but not so directly. So I don't know how many of you are into cosmology, but there's one equation that summarizes practically all of cosmology. This is the metric written in a slightly different, unusual way, but it's practically the usual one. It tells you what is the background evolution of the universe. It tells you what is the perturbations at first order, a linear order, depending on these two potential psi and phi. So it doesn't matter whether you really are interested in the metric on cosmology, but just to say that essentially what we do in cosmology since many years now is to understand, is to write down, is to compute the various unknown quantities in this metric. If you know this metric, you know the geometry of space-time at all epochs. And that's what exactly cosmology is trying to do. Very ambitious. Now, in fact, it's an extremely simple equation. It depends only on the expansion rate h, on two perturbation potential, psi and phi, which tells you how gravity is acting, and on this parameter, which has to do with curvature, the space curvature, the curvature of space surfaces, and h naught. It's an extremely simple equation. So cosmology is an extremely simple science in the sense that it tries really to answer very simple, basic, fundamental questions. In practice, to write down a question solution for these 3 or 4 unknown quantities. So cosmology is an ambitious science which tries to answer big questions. Is space flat? Is omega k equal 0 or not? How is the universe expanding? What is the function h of t? How are perturbations growing? How psi and phi depend on time? Is GR correct at all scales and epochs? Means, is psi equal to phi or not? All these fundamental big questions are embodied in this simple structure of the space-time metric. Okay, if you ask this to many cosmologists, including me, including most people, say the first answer that comes to our right, okay, but essentially we know most of this, right? There are so precise answers. If you take, for instance, Planck or other experiments like that, you can read a list of parameters. I don't want you really to read them, just to appreciate that there are lists of parameters. And you can find very precise measurements. You can say, well, we know omega curvature is 0 plus minus 1%. No, percent you cannot say it's 0. It's 0 plus minus 0.01. And H naught is known to 3.45%, although there's the famous tension. You can read almost every in tables like this, using Planck or other experiments. So sometimes we say that cosmology is already into the domain, into the direction of precise science, which is true. We have very good, very precise constraints on most of these parameters. We can say what h of z, what h of time is, because we know what omega matter is with some error. We know what omega dark energy is. Oh, I say dark energy. Sorry, what omega cosmological constant is. And so we have precise answers. But are they accurate? So we have many interesting, precise information constraints on all this. But essentially, all of them are obtained assuming a specific cosmology. And this specific cosmology is often lambda CDM. And if it's not lambda CDM, it's maybe W CDM. If it's not W constant, it's W plus a derivative. It's always a very tiny, as mathematicians say, zero measure class of models in the landscape of all possible models. I'm not criticizing this. I do, and we do that all the time. We have to do that. Sooner or later, we want to measure some parameter of some theory. But now the point of this talk is whether it's possible to do something, maybe not everything, to do something without necessarily at every step assuming a specific cosmology. And I try to show that you can give some answer to some of those questions without being too specific about which cosmology you are using, which means whenever I finish with this program, which maybe will take another life, we will be able to say, yeah, the curvature is 0.01, and that would be really that, and not, yeah, it's 0.01 if you assume that the inflation is right, the universe is Gaussian, lambda is this, that matter is that value. So not hasting to say all the conditions under which you got that value. All right, so there are two themes in my talk. The one is increased precisions by using multiple traces and nonlinear scales, and increase accuracy by keeping assumptions as minimal as possible. That's the plan of my talk. And I have to start with a disclaimer, because I use often the expression model independent, regardless of cosmology. And of course, I say use this expression because they're quick, simple, and I guess intuitive. But of course, there are many cautionary words one has to say. There's no way you can be totally model independent. Every time we do anything, there is some modeling. Even if the model of the instrument you're using, it's also model. It's also some parameter you must use, because you must claim you know what your instrument is doing. So even just talking about the theoretical assumptions, of course, I'm assuming homogeneity in the isotropy on large scales, although this one can be, in principle, relatively straightforwardly also be overcome or generalized. Assuming that linearity is often a good approximation, or at most some mildly formal nonlinearity. Assume, for instance, supernovae 1A can be standardized or are standard candles. The idea is that, of course, we must assume many things, but hopefully those things are not totally directly related to cosmology. So I'm assuming something, for instance, that supernovae standard candles, which at least in principle can be rejected or confirmed by using astrophysical tools, and not necessarily have something having to do with cosmology. So I'm trying to do something without assuming cosmology, but assuming many other things. I just try to see if I can minimize the number of assumptions. That's what I try to do. Specifically, I will not assume a cosmic expansion rate, a particular one, not even a parameterized form. I'm not assuming any about perturbation growth, a linear or mildly nonlinear level. I'm not assuming a Bayesian scheme. You will see this along the way, but just to say that I really, when I say model independent, I mean something specific, not just everything, but also not just, using parameterization which are not related to physics, and people sometimes say they are model independent. No, I really mean that I don't want to assume a specific cosmology. All right, cautionary tale. Consider a very simple universe formed just by pressureless matter uncoupled, no modification of gravity, just matter, ordinary matter, including dark matter, and something else in flat space. Now, this something else, of course, could be dark energy, and true already, but it's really something else. We don't know what that is. Just say, let's assume the universe contains some unknown component. The question of state of this something else is related to the expansion rate with some simple relation. That's the question of state. But the point is that even a perfect knowledge of this is the expansion rate, h of z, how the universe is expanding in time. Even a perfect knowledge of this is not sufficient to obtain W at every time, at every epoch. You need also omega matter today. But what you get from distance indicator from supernovae is E, that means H, not this. When you say we measure this or we measure W, be careful, because always that means we measure this, we measure W, if we make some parameterization. That means strong assumption. Like all the data can be represented by two numbers. And this is our hypothesis. It's nothing that is told us by the data. So conclusion, either you know omega matter, obtain W, or you know W. For instance, you assume that W is constant and obtain omega matter. And this is the simplest one, because if space is not flat, you also need curvature. In fact, distance indicator don't even tell you what h is, tell you what the distance is. And from distance to expansion, there is some integral. Same problems, much worse actually, if you test gravity. When you say we test the gravity using some indicator, there's always some parameterization and some strong assumption about cosmology. So that's why I think there are problems in doing that. I mean, whenever we say we know the question of state, we should be aware that that depends critically on many assumptions, which unfortunately are not independent of cosmology, not assumptions of whether stars are isolated system or whether the halo is spherical, but really assumptions which have to do with the things we are trying to measure. All right, so the theme one, if you remember, was increased precision by using multiple tracers and nonlinear scales. Now, quick recap for the few of you that are not particularly interested in cosmology. Standard candles are, whenever we have an object that we know the luminosity, we can measure the flux, because the flux is what we see at the telescope, and therefore we can get the distance, or what we call the luminosity distance. If we know the luminosity distance, we know that this is related to cosmology, the expansion rate, this famous h, which I introduced at the beginning, through a simple integral, which actually is not as simple as this, because there is also curvature, but I try to simplify because that's not important now. Just to say that every standard candle is something that has a fixed luminosity. Why is fixed? Well, because we have expectation and calibration that tell us that this source of this class of sources, supernovae for instance, are indeed standard candles. They always have the same luminosity, and if not, they can be corrected in such a way that at the end we know what the luminosity, the intrinsic luminosity is. So this is known, this is measured, and you get this. That's how we do cosmology at the background level. So you certainly have seen plots like this, Nobel Prize plots. What do we do with standard candles? We measure the magnitude of the flux here. We measure the distance, the redshift Z here. We construct a Hubble diagram. This is the one on 97. This is large redshift, which are the one of cosmological interest. These are only used for calibration. There are only a few of them, 7 in 97, 40 in 98. And this is the Nobel Prize plot, which you discover, which the accelerated expansion has been discovered. All the supernovae are dimmer than you expect in a universe without cosmological constant. Then a few hundreds in 2010, and then of the order 1,000 today. It's the same Hubble diagram with more and more objects, more and more supernovae. That's essentially how we know anything. We know something about the expansion of the universe. There are other tools to do, but this is still the basic one, magnitude versus redshift. And you fit this according to your cosmological models. Now, this is roughly 1,000 or 2,000 supernovae nowadays. But this research is so important that the people in the future is planning to collect hundreds of thousands. At the Vera Rubin Observatory, the LST survey plans to measure this density of supernovae in this volume, according to various hypotheses. Don't really read the numbers, just read the conclusion. We plan to have thousands to 100,000 supernovae per redshift beam, which means we can have 100,000 at this redshift, at this redshift, at this redshift, and so on and so forth, and perhaps even a bit beyond. So in the next few years, we go from a few hundreds of supernovae to hundreds of thousands of supernovae of type 1a, hopefully. Of course, there's always a more conservative and a more aggressive scenario. So can we use this abundance of data to do something more than what we've done so far? So luminosity of standard candles gives you the luminosity distance, it gives you cosmology. But not only that, we measure other things about supernovae. We measure position in the sky, we know where they are, and we measure the scatter around the mean. You see this scatter, which I showed you in this scatter here. To what is due this scatter? Whether it's a scatter at all. We'll discuss that in a second. If there were perfect standard candles, every object at redshift 1 should have exactly the same total magnitude. So beside the observational error, there is an intrinsic scatter that could be also give information. So in fact, position of a source in the sky is a tracer of large-scale structure. If there are more sources there than there, it means there is more clustering there than there, and therefore I can use the supernovae themselves as tracers of large-scale structure. And the scatter around the mean, I discussed that now, gives us another important information about the supernovae, the peculiar velocity. So the idea is that we pass from a situation in which we had individual sources disconnected in the sky, one here, one there, and we use only the information about the luminosity of the source, how much light they emit, to a situation in which we go to a field of observations. From every supernovae, we can measure the peculiar velocity, of course, only the direction, along the direction of the line of sight, and the correlation between positions, whether there are more here or there or there. So going from just using supernovae as points to use supernovae as field. And field of two things, position and velocity. Let me discuss first the velocity, which is the most interesting part of the story. What we observe is the redshift, but the redshift is the recession of a source, is the sum of the cosmological recession due to the expansion of the universe, plus a correction, plus a deviation, a correction, which is due to the fact that the source itself will be moving probably in some direction, just because field's gravity, local environment is trying to go there or another direction. We cannot distinguish the two. We just see the total velocity of this object in the sky. So we see the sum of the cosmological redshift plus the projection along the line of sight of the peculiar velocity. And there's no way we can distinguish this. We just measure a total sum. So two supernovae, which are exactly the same physical distance, will appear to us having a different redshift just because they have a different peculiar velocity, each one at their own. So the luminosity distance that we measure can be written as the luminosity distance as a function of the total redshift, which can be divided in two pieces. This one is the cosmological one, and this one has to do with the scatter. And the scatter, the luminosity distance, is related to the peculiar velocity. So one component, at least, of the scatter, certainly not the only one, has to do with the intrinsic peculiar velocity of the source. And the idea is to use this extra piece of information. How do we go from, but we observe only luminosity. How do we go from luminosity to velocity? Some years ago, has been shown that if you have a velocity along the line of sight, v, then this induces a change in the luminosity distance, which is exactly the one I mentioned in the previous slide, this change here. Sorry, now using capital letters for d, but it's the same quantity. Related to the velocity induces a shift in the luminosity distance, which is related with this conversion factor. But there is a relation between flux, which astronomers prefer to call a paramagnitude, and the distance, which is this. This is exactly the same relation, flux versus luminosity, we see a moment ago, but written in the way astronomers prefer to write it. And because of this, any change in the luminosity distance induces a change in the magnitude. That is exactly the scatter we see. The scatter we see in the double plot is a scatter in magnitude. Putting together these two equations, we have a relation between what we observe, the scattering magnitude or in flux, and the velocity along the line of sight. So this is a relation which allows us to use the scatter of the Hubble diagram to infer the luminosity, to infer the velocity field. So now you have to imagine that in this field of sources, supernovae, we have luminosity, we have velocity, and we have position. We have actually 3 pieces of information. Now comes the critical point. This peculiar velocity field, at least in the linear part of it, is not a random quantity because it's correlated with the density contrast, which is kind of intuitive, because if you have more matter in some region, then sources, including supernovae, tend to go there. If there is less matter than the average, they tend to go outside. So whether there is the linear component of the peculiar velocity in one region of the universe has to be associated with the local clustering in that place. So there must be a connection between the velocity field, the peculiar velocity field in the linear regime, and the density contrast. And this is actually given by ordinary standard linear perturbation theory. The velocity along the line of sight is related to the density contrast in the galaxy component through some factor which are geometric, the cosine of the angle, but this is in Fourier space, so this is now no longer, so this is a field in real space, but from now on, all the fields will be converted automatically in Fourier space, which is what we normally do in cosmology. So there is a wave number k. So there is some geometric factor, which are not particularly interesting. There is a beta, which is an important parameter, which is related to the growth of perturbation and the bias between galaxy and dark matter, because of course we don't know whether we see galaxies and we want to relate the galaxy to the dark matter distribution, and there is an unknown factor in that. And H, most important, which is one of the quantities we need. So this relation here has to do with conservation of matter, has nothing to do with gravity per se. So in fact, as far as I know, it's valid in essentially all models of modified gravity, because whenever this is modified by an extra scalar field or something, and this scalar field, if it is introduced to explain modified gravity, always it'll be very little clustered on small scales. So if there is a correction to this equation, it's supposed to be negligible on sub-horizon scales, even in modified gravity models. I'm sure you can come up with a theory in which this is modified. It would be interesting to include that modification. I wonder whether maybe the process can be repeated again, but for all the most common modified gravity theories, this equation remains valid because it has to do with conservation of matter, with the fact that galaxies and supernovae don't just appear or disappear in the universe, and not with the force of gravity. All right, so we use this relation to connect this measurable velocity field to this quantity, which is one of the quantities of interest, and H and all the other parameters. So now you understand the main point, I think. We have several random fields in the sky. For instance, we can look at the position of galaxies. That's what we normally do. We do all the time, clustering of galaxies. And this would be a delta, density fluctuation in the galaxy field. And now we have another field, which is the velocity associated to standard candles. Notice, there have to be standard candles. You cannot repeat this with any source because you need to know the scatter around a value which is supposed to be the same universal for every source. So this is clustering of standard candles. So we have 2 fields. And with 2 fields, you can get 3 correlation functions. Delta, delta, star, you need to put a star because they are Fourier quantities, so they are complex in general. Delta V star and V star. Forget about the star, it's not important. There's a correlation of density contrast with density contrast, a correlation velocity with velocity, and a cross correlation density and velocity. Now, there's plenty of mathematics here, but all I want to say is that they're all related to the matter power spectrum, which is a crucial quantity, of course, because it tells you how matter is distributed, and by a bunch of factors which have to do with the bias, with this beta parameter, this is called redshift distortion. This is very kind of familiar, at least in some part, to everybody doing clustering, but it's probably pointless if I start explaining every single thing. What I want to say is that in this way, we have an extra way to measure this combination of parameters. There are a few things which I will not go into any detail. There is some smoothing here due to the fact that we try to model the smoothing of the power spectrum due to the velocity of the sources, including the galaxies. There is a noise, source of noise, which is just defined to be unity just because of the way I normally write this. Otherwise, it would be 1 over n. So again, I don't want to go into much detail, just to say that we can observe all this combination of parameters. Now, look for a moment at this one here, delta star. This is the one we normally use in galaxy clustering. This is what is called redshift distortion. This is the bias, this is the power spectrum. If we had only this relation, would be impossible to disentangle the bias from the power spectrum, unless, again, you start making assumptions. For instance, unless you say, well, we know the shape of the power spectrum is the one provided by inflation. We know what the bias is because local and because n-body simulation based on lambda CDM tells you that the bias is around unity or is not much tendency to grow with redshift and so on and so forth. So in order to disentangle the various pieces, you have to make many assumptions on this or that. But if you now have several independent pieces of information, well, not independent, related, but different pieces of information, then you can hope to measure, for instance, this beta because it appears there, it appears there, it appears there as well, but in different combinations. So you can disentangle the two things. All right, so the point is that you have two random fields, at least two random fields. You will see now there are more than that. Three correlation functions. You can make a likelihood function with all these fields, and you can construct a correlation matrix, which depends on the galaxy-galaxy, on the velocity-velocity, and on the cross terms. So we're adding statistics to the problem, just using what essentially we already have or will have soon in the future. Remember, I started to say we need tens of thousands of hundreds of thousands of supernovae. If you have only a few hundreds, of course, all this is pointless because there will not be enough to make. Remember, we're normally using galaxy clustering millions of galaxies to make this. If now supplement millions of galaxies with 1,000 supernovae, nothing happens, just negligible. But now in the next few years, we can supplement millions of galaxies with hundreds of thousands, maybe in a million supernovae with well-measured properties. Then you can continue playing the game. You can use supernovae themselves are tracers directly of position, not just the velocity. I'm discussing velocity because it may be more unusual way of treating supernovae, but supernovae themselves trace exactly as galaxy, the large-scale structure. So now you can have three fields, delta supernovae, delta galaxies, and velocity of supernovae. And therefore, you have 6 correlation functions. Again, I don't want really you to read all the numbers here, just to say that now you get a correlation matrix, which includes correlation between galaxies and galaxies, supernovae and supernovae, velocity and velocity, supernovae and velocity, and so on and so forth. And of course, if you have more tracers, but I don't want to go in that direction, you can increase even more. And the more you put there, the more information you get, up to the point that, well, up to several limits. But of course, if you start taking galaxies and then divided them in 10 subclasses to use them separately as tracers, then the 10 subclasses will have 1/10 of the density. So of course, you have more independent tracers, but there are much less statistics, each one of them, so it's not obvious that you really gain a lot. So let's stop at this level now. Let's deconstruct this matrix. This is what most often is done, the large-scale structure clustering using only galaxies. That's what, for instance, Euclid will do. Well, we'll do other things, of course, but that's the main part of the Euclid. Euclid's satellite will be launched this year to measure large number of galaxies and images. So it can do more than that. It can do lensing. But as far as concerned galaxy clustering, that's what essentially Euclid will be doing to a fantastic precision. That's what people normally call multi-tracers, use not just galaxies, but other sources, for instance, supernovae themselves. So in this case, you do clustering of velocities, but using different tracers. It's a well-known technique. This is what I introduced a moment ago, the 3×2 method using the velocity, and altogether is what the 6×2 will be. So it combines essentially all the information you can retrieve if you have a sufficient number of supernovae, or standard candles can be applied to any standard candles, even gravitational waves. We generalized to gravitational waves recently, or to other tracers. Now there are many complications. How much time do I have? 1 hour, right? Or 50? Okay, no, just to be sure. All right, so now comes a bit of complications. Unfortunately, some of these will be maybe not so interesting for those of you not particularly concerned about cosmology, but I have to mention them. So we do not have access. I'm talking about K, mu, angles, wave numbers, position, but we don't have access to distances. We have access to redshift or angles in the sky. So we can convert angles and redshift to wave number or angles, mu, or mu is the angle between the wave vector and line of sight. but only if you know the cosmology. So whenever you see a plot showing you P of k, power spectra as a function of k, this can only be obtained if you assume a cosmology, which is totally fine. It's not a mistake. Just to say that next to the information of the power spectrum should be written in the caption, this has been obtained using such and such a cosmology, what is normally done, of course. But if you don't know the cosmology, you have to take into account that this is just a reference cosmology, it's not the true one. For a generic cosmology different from the reference, you have to correct k and mu according to some equation which have been derived many years ago, which are called Alko-Paczynski effect. This is well known. I just say that we need to take care of this problem here. And this you see when you do this transformation, you have again h and you have again d, the distance. They enter as parameter of this transformation, which is obvious because in order to convert redshift into a distance, you have to know what is the velocity distance or the angular diameter distance, and also actually you have to know also the Hubble function h. So this is taken into account, not just in our method, but in general, just to point it out. This actually plays an important role. Now comes one of the important points. So now we collected all this data, or we will collect all this data. What do we do next? The standard approach is, okay, let's parameterize cosmology. Let's assume there is matter, curvature, maybe a sigma 8, which is normalization, maybe a growth rate parameterized by gamma. So you essentially decide that cosmology is lambda ЛCDM, except you don't know some parameters. You don't know omega matter, you don't know exactly the growth rate, but you parameterize with a single number. You could add the question of state of the dark energy. And you can do many things, but always first choosing the cosmology and then parameterizing it. Or you can do something much more model-agnostic and use all the parameters you can use allowed by bin data. If you can bin your data in 20 redshift bin and 20 k bins, then you have 400 bins, k and z, and then you can use 400 parameters. This looks like a mess, but you can do that, and we showed that you can still get some interesting information. So the choice we make at this point is not to use the standard parameterization, which refers to a very tiny set of models, but to use the maximal set of parameters possible. All the power spectra wavebands for every k and for every wave number and every redshift, which means essentially we divide all information into space and time bins without trying to connect one with the other. Every cell in space and time is an independent quantity, an independent parameter in your big fit. We do the same for beta, which is again this ratio here. And then there are a few other factors. This depends on the Alko-Paczynski effect, includes h and the distance. And there are a few other factors which we cannot eliminate, some parameters, for instance, the dispersion velocity sigma, which introduces a smoothing. That again, the best you can do is to assume that that is unknown and unknown differently in every redshift bin. They don't depend on k. So to summarize, to synthesize, what we try to do at this point is to try to use the maximal number of parameters allowed by bin and data. You can find other combinations, but there will be no more information because every other combination, if it is the maximal set of parameters, can be converted into this. So you can prefer to modify in a different way, but at the end, they can be directly one-to-one converted into each other because this is the maximal. The only choice you have to make is how you want to bin the data. And you try to make this as much as possible before running into other problems. I don't want to discuss them in detail, but of course, just to give an intuitive understanding, if you make too small cells, then they start being heavily correlated to each other. So there is some discussion about how to bin the data, but I don't want to go into that. This important parameter, eta, which I call eta, is related to h. In fact, it's related to h and d. Luminosity distance also can be written in terms of angular diameter distance. This is just a reference value, don't play any role. So it depends, in fact, on both. But D can be very well measured by Hubble diagram of standard candles, the standard approach, which, as I told you before, gives you the red tree, not h, not the question of states, but distances. So distance are actually very well measured, and it's difficult to beat this method, direct measurement to the Hubble diagram. So I can easily, for simplicity, I can assume that this D is actually well known to 1% precision, and therefore focus just on h. At the end, actually, I will lift this restriction just to make it more general, so it doesn't play a big role, just to say that's what I do for the next few slides. All right, so we can again summarize what we did so far. In the standard approach, you restrict to very small number of parameters. Now, the number of parameters look the same, but of course, no, this means one parameter for every bin. So there could be easily 200 of this and 200 of this and of this. This is one parameter, one parameter, one parameter, and so on and so forth for all the bins. So it's a large change, it's not just a manual one. So the standard approach has a high precision because you restrict to very few parameters. So you get very tight constraints, but of course low accuracy because you make strong assumption. We tried a different route, alternative, orthogonal, I would say. Low precision, we get certainly weaker constraints, but we make a minimal set of assumptions. Of course, at the end of the day, you would like to maybe have the advantages of both, and we'll say something about that later on. So the story so far, okay, essentially already summarized. This set of parameters completely specify the correlation at any linear wave number, angular, cosine nu, and redshift z, and the low measure of h of z without assuming any cosmological model. H of z is essentially included inside this eta. Okay, next two slides are very boring because what can we do now? We don't have data, right? I just say that we can get data in a few years from LST. We can already play with the data we have now, but it's not particularly useful because it really depends on having many supernovae. So we cannot play with real data, we play with forecast. So the next two slides are very boring tables, just to tell you that we did this exercise. We try to use all this together, make a classical Fisher matrix analysis, which is the first step you do when you're trying to forecast what the experiment will tell you in a few years. So our question was, given that we have Euclid, for instance, or DESI, or some important experiments in the next few years, given that we know what the volume is, what the sensitivity is, what the noise is of those experiments, how can we measure those parameters? And the technique you use normally is the famous Fisher matrix analysis, which is just tell you how the signal depends on the first level on the parameters. Essentially, it's just measuring first derivatives of the signal with respect to parameters. So you know how sensitive you are. You put together in statistical methods, which you call Fisher matrix, and you end up with forecast. Prediction of how this and that parameter can be measured if the experiment is really carried out. So there are many tables that I will not certainly spend too much time, just on one of them. The error on delta H of H, which is the expansion rate of the universe, can go down in the best case, 6 and 2 to 3% in various redshift bins. Now, this redshift bin now a bit limited because we want to have supernovae and galaxies, so we cannot go beyond that. So we have to restrict ourselves to relatively small redshift. But of course, if you have surveys with more supernovae, and particularly also with gravitational waves, you can do below, quite farther away. And this tells you how delta H over H goes down, how it improves, going from the standard analysis, no, there's not even standard analysis, going from 3 times 2 to 6 times 2. So you see there could be an important effect depending on some uncertainty, depending on the fact that we don't know yet what the bias of the various sources is. There are many unknown parameters. We take all of them into account. We vary all of them. That means we consider what the constraints are when you vary all the other parameters. And at the end, you can reconstruct the expansion to 3 or 4% in the best case. If you have 10 to 5, 10 to 6 supernovae with LST. But that's, of course, you don't have to finish here. This is our general approach. Now, nobody prevents you or me to now go down and say, okay, but what you can say really about lambda CDM, because we're also interested in that. We also want to measure mega matter, mega lambda, if we believe in lambda CDM, and there are good reasons to believe in it. So now you can take all this big matrix of information, project, restrict onto the parameters you want. So you can see this method in two ways. Give an answer which doesn't depend too much on cosmology to some question, like for instance, what is H, a redshift 1 or 0.5 or 6? Or you can see as a way, a pre-processing stage. You take all the information, you build a big matrix that contains the maximal amount of information. This is general, it's universal, and now everybody can take that and project onto their preferred set of parameters. So you can use that to use information on modified gravity, on lambda CM, or whatever. Of course, we did that exercise a bit. And again, there are plenty of tables like this in our plots, like this in our paper. And this is just to say that if you include also, for instance, Planck, then you discover orthogonality. So you discover that you can restrict already with these 6 times 2 methods. But if you also include other experiments like Planck, always based on particular cosmology, you get to even much higher precision. So again, this is the moment in which you pass from high accuracy, low precision situation to the other way around, to high precision and relatively low accuracy, because you're restricted to a particular case. You don't have to decide to do either or one. You can do both and be happy with it. And now in the last 10 minutes or so, I want to try to see how much we can go in the direction of accuracy and precision, to have both. And as you maybe remember from my initial theme of the talk, which was increasing precision and accuracy, I mentioned nonlinearity. Now, the best way, the most straightforward way to increase the amount of information is not to stop to linear scales, because one that I didn't emphasize enough in all what I did so far was that we can use all this information on clustering of galaxies and supernovae easily only to some level of some like 10 or 20 megaparsec scales, because if we try to have information on smaller scales, which is the scale of clusters of filaments, then you have to know much more than just the evolution of the universe. You have to know how galaxies form, whether there is feedback, whether there is baryonic physics, lots of complications. Nonlinearity, and not just nonlinearity in gravity, which is already complicated enough, but nonlinearity and other phenomena which are hydrodynamical in nature. So there is linear scales, very large scales, which everything is ideal somehow. There are intermediate, mildly nonlinear scales, which you have to do nonlinear gravity, but still the hydrodynamics part is not important. And there is the extremely complicated, very small scales, which essentially you can do only simulations to compare to reality. So I did the first part linear, and now move into the mildly nonlinear regime, which we can generalize gravity to higher order, but still we don't have to worry, hopefully not too much, but a bit we have to, you see, with baryonic physics. All right, so the idea is to go nonlinear. This is certainly not our invention. This has been, I'm working on a body of work in the last 30 or 40 years, which has been heroic efforts by several people, and essentially ended up with this thing. Ended up with the fact that power spectrum of galaxy depends on the linear part, but can be corrected by various terms which are called one-loop correction, ultraviolet correction, and also infrared correction, which I'm not showing. There is also some noise. Now, this is what essentially I've been talking so far, and this is just an overall smoothing which tries to model the very high, very small scale and normally doesn't play necessarily a big role. This is the kind of change. You go from the linear regime, which is this blue line, which is okay on large scales. These are large scales. Small k means large scales, which are okay on small scales, but certainly not okay, actually very much corrected when you move beyond this 0.1, which is a reference value. This means scales of order of 10 megaparsec, 1 megaparsec. These are scales of order of 100 megaparsec. So we certainly need the correction if you want to move beyond 0.1, which means if you want to use information on small scales, you need to introduce this and perhaps even higher order terms. Now, these expressions here are relatively complicated, and we'll discuss briefly a moment later on, but I don't want to go into much details. But the point is that it's not just a minor approximation, a minor change. Looks like a relatively small difference. Actually, it's not, because it's a logarithmic scale, so it's actually a big one. But even if it looks small, it's not small for the simple reason that how many modes, how many k modes are in a Fourier transformation, how they increase with k? Well, this is a three-dimensional problem, so they increase like k cubed, which means if you double the range of k, you multiply by 8 the number you have data. It's like really collecting 8 times more galaxies or bigger volume than restricting to linear scales. So it's a huge advantage, at least in principle, when you increase even a little bit, even if you go from 0.1 to 0.2 in k, there's a huge increase of information. However, there are many problems, because adding these new terms introduces many new uncertainties, and we would like to keep to our philosophy of being as possible model agnostic. So this is high-order perturbation theory. It's been developed by many people in the past. I'm certainly apologies because I'm sure I'm forgetting several important contributors. And essentially the result is that you can write down more and more complicated expression, which this P1 loop is written as integrals over kernels, multiplying power spectra. They actually don't look very complicated now. They are, but they are not, because actually most of the information is compressed. This S, this F, all these things themselves are other functions of the wave number. So it's a complicated business. Fortunately, it has been done for me and for all of us by valid cosmologists in the past. So we're just using most of the information which is already in the literature. There is various, this is not the only way to write it down. For instance, these counter terms are written in different ways in the literature. There's not universal consensus, but they certainly depend on at least 3 new parameters. There's a host of parameters which you can barely read. There is a BG, a big gamma, a C0, a C2, is plenty of parameters because we need them if we want to be general. These are kind of generalized bias parameters, which means they tell you the correlation between the underlying dark matter distribution and the galaxies. And a linear order was only one bias parameter, but a higher order, you have to introduce a second order bias, a bias that depends on tidal fields, a bias that depends on many other things. So there are many other hidden parameters in this expression. And this is only for the PGG, but you remember, we wrote down 6 correlation functions. So in principle, we should generalize to nonlinearity this, that. Okay, these have not been done yet. I only restrict to the first line. Some work in this direction has been done recently, which they try to generalize a bit to also PPV, and I will not discuss that. I will just stick to this. So all we did now is to focus only one part, the most interesting one perhaps, the correlation of galaxies, and see what the extra information on the nonlinear scales can induce. As I say, the problem is that we get lots of more information, but we also get more uncertainty because there are several new parameters, at least these 4 new, at least 3 new bias parameters, each one of them unknown, each one of them can be arbitrarily different from redshift to redshift. Fortunately, they're not expected to depend on K. And this is another parameter, it could be 1 or it could be 3, depending on how general you want to be. So we have more modes, more data we can use to smaller scales, but also more uncertain parameters. It's not obvious who wins. So we did this exercise, but before doing that, there's an important point. Only using this extra nonlinear part, you can measure the bias B1. If you don't introduce this part, this bias B1 is unavoidably multiplied by the power spectrum itself. The bias always go together with the power spectrum. You cannot disentangle a linear order, but you can disentangle at higher order. Why this is important? Because this beta, I don't have a blackboard, but if you remember, this beta was related to the growth and the bias is the ratio somewhere. There you go. This beta was related to the growth F and the bias B. If we don't know the B, we cannot get F. So we can measure beta, but we cannot get F. And F is, I don't know if you forgot the expression for F. As usual, these are very common to everybody doing cosmology, but I understand that. So F is the growth of fluctuation. If you know F, you know how fluctuation are growing in the universe, which was one of the basic questions that I asked at the beginning. All right, so only going a second order, higher order, you can disentangle F from beta, which means you can measure, you can disentangle B from the power spectrum, which means you can measure, since you measure F, you can measure directly. Since you measure beta, you can measure directly F. So just to simplify, only at high order, you can answer one of the 4 basic questions, how perturbations are growing in the universe. All right, again, there could be many plots and tables to show you. Again, this is just a forecast, not real data. We produce a plot in which you show how delta H of H errors improve, so decrease, when you go decay max from the linear 0.1 to 0.2 or 0.25, depending on how much you believe your linear expansion. And the error decreases by several factors, so almost a magnitude from 0.5 to 0.05. That means from 50% to 5% when you increase decay max from 0.1 to 0.25, even taking into account the host of new parameters. And now comes the last point. I hope I have time, because that's not the main part. Because once you start going high order, then you should try to retrieve much more information than you started with. Once you decided to go to higher order in the power spectrum, which just tells you what is the power spectrum as a function of a wave number k, or a vector, you can now at the same level, you should actually at the same level include at least the bispectrum, which is the generalization to 3 points in space. It depends on 3 vectors that form a triangle. So why this power spectrum only depends on a vector, on position, on 2 points, that is the correlation between 2 points. The bispectrum is the correlation, is the third order correlation, is the correlation between 3 points in space. In Fourier space, it depends on quantity, it depends on K1, K2, K3, provided they form a triangle, so they have to have the relation that satisfies a triangle. Fortunately, the bispectrum can be taken at 3 level, which means you can also add high order correction here, but this is high order per se. So it's more consistent to do first high order in power spectrum, but stay at the first non-trivial order in the bispectrum, and that's what we did. Fortunately, the good news is that this doesn't depend on additional parameters. All the parameters that enter the bispectrum are already there, except some noise part. The bad news is that this is a 3 level, which means does not include high order correction, which means you should stay on smaller scale, on larger scales. Otherwise, you get high order correction, which are terribly complicated. So while for this we can perhaps hope to reach even 0.25, which means relatively small scales, a few megaparsec, for the bispectrum, you have to stay on large scales. Otherwise, you will not be able to trust your results. So that's what we did now, the exercise, using power spectrum, bispectrum, lots of parameters. And we also included something which is relatively new, 4 parameters which go beyond the Einstein de Sitter kernel, which is something that probably you will not want to know anything about, but in case I can answer questions. So what the final results, and I really conclude, is that if you combine P power spectrum with B bispectrum, you get very much focused regions, again, allowing for the almost maximal freedom in your parameterization. And now you can get both the expansion rate and the growth rate to precision of order a few percent in every redshift bin, which means not only integrated, but at this bin, at that bin, at that bin. That means you reconstruct. So this is H versus F, this is H versus D, and you see how it's important to combine the green region with the blue region to get a very narrow red region. And then you can produce other nice plots, like what is the predicted error on the linear underlying dark matter power spectrum, for instance, equal 1. You can get very precise error bars this way, up to relatively large K. And H as a function of redshift, F as a function of redshift, with a more conservative or a more aggressive choice. And in some regime, you can go down to 1 or 2%, both for F and H, with a minimal number of assumptions. Remember the big questions we asked at the beginning. Is space flat? Now you have H and D, then you get omega K. No cosmology involved, it's just pure geometry. How's the universe expanding? Well, I just show you that you can get H of Z. How are perturbation growing? I just show you that you can get F of Z for various redshift range. Is GR correct at all scales and epochs? No, sorry, I didn't tell you anything because it's not part of this talk. But if you're interested, we also address this question in other papers in the past. We try to apply this model-independent procedure also to a direct test of GR. So I show you that you can get some answer for the most basic questions of cosmology in a way which is relatively, of course, not totally independent of cosmological assumptions. Conclusions, well, models are, of course, important. Please don't take my statement as there's no point in making models at all. Of course, after some point, we want to get measurement of precise parameters because we like modeling. We need to model them. So you can take this as a first general step. And then now you move to more detailed answers. So, but there are limitations, assumptions you have to be aware. Many questions, like is space curvature 0, is gravity modified, are model-independent statements, the question of state-dark energy. No, they are not. They rely on particular assumptions. But in some cases, you can do something without assuming cosmology. For instance, H of Z can be measured to a few percent. Other parameters, the beta parameters, P of K, you can use that with any standard source, for instance, standard science, a paper on that. Going nonlinear improved statistics, which is well known, of course, and allow to measure the growth rate F. And we found that including bispectrum, you can bring constraints down to practically 1% in various redshift bins, again, in the same philosophical spirit of trying to reduce the number of assumptions. All right, so that's it on my side. Thanks a lot for listening.
So I guess that there will be some questions or comments.
So you mentioned that. So you mentioned that you're moving from a very small set of parameters for when you decide on a particular cosmological model to a very large set of parameters, right? So in this sense, are you not worried that having too many parameters would add noise, basically, to your underlying modeling or measurements of these H of Z or?
Okay, thanks for the question. By the way, I just remember now that, of course, I mean, I'm making a colloquium, so I try to be general, kind of intuitive. I try to not to go into many details. So I totally forgot to say that, of course, we are not the only one doing this. For instance, here in Barcelona, Licia Verde and Hector Gilmarin and other people are working in similar direction, many other people. So I just try to present my view. I'm really sorry that I didn't emphasize this earlier, but I try to speak in a more general way. So, of course, there are many ways of proceeding in this direction. You can be extremist and try to really make as much as possible. You can say, well, but actually we know many things. For instance, we like inflation. We know more or less the shape of the power spectrum, so we can at least use that and restrict our attention to other parts. So it's obvious that I try to see what we can do in a sort of extremist, let me say, way. But I'm not an extremist at all, so there are many ways to reduce or improve in various directions. And of course, many of the researchers are working in this way too. Which comes to your question. Of course, that's the exercise. We have to see. It's not obvious that we gains. In fact, when we started doing this, I was very skeptical. I told my collaborators, if we introduce all these parameters, we blow up all information. But it turns out, and that is not so much. And now if you tell me why or so, well, I will not be able to give you a precise answer because, it's a list of 20 parameters plus all the k-dependent ones. So whether, how they're correlated in which way is very difficult to say. But the point is that, actually the main point is maybe this one. This H and D, which I focus on, but then there was also F and other things. H and D, which are some of the most interesting quantities, the expansion of the units and distances, they are introduced in the question because of Darko-Pachitsky. So in fact, all the information is in Darko-Pachitsky stuff, in the fact that you see that a universe which is isotropic, which should be isotropic, a power spectrum which should be isotropic, will appear not isotropic because you're just using the wrong cosmology to convert your redshift into positions and angles. So, the Darko-Pachitsky was that we know that the universe is isotropic, statistically, of course, and we use that information to say that if your cosmology is wrong, then you get anisotropy that tells you that you're wrong, so you recover the correct one when you finally find the isotropic, statistical isotropic power spectrum. So that's where H and D comes into play. And apparently this is not spoiled almost at all by the introduction of these extra parameters, because it's a kind of intrinsic, fundamental, basic principle that we have to satisfy. Otherwise, I don't know, you just have to see. And many other quantities, for instance, in the first exercise, the one, when we got some information about F, the growth rate, we were very disappointed because we found error of 20, 30%, completely useless. It's only adding the bispectrum that I'm sure this is known to other people as well. These are many people are working in this direction to show that the bispectrum contains. So that we ended up finding interesting constraints only after doing this and only discovering that you need to assume other things. That's no a priori answer to your question, I would say.
More questions?
With your supernovae plot and distance redshift plot, you mentioned some of the error budget comes from the velocity, peculiar velocity, but I observed in higher redshift, the errors are actually larger, but peculiar velocity's error budget there is actually smaller. So there should be some other contributions which are much larger than peculiar velocity.
Definitely. I only discussed the linear peculiar velocity part because it's the one that goes direct into the power spectrum formulation. But on top of that, there are errors, which means part of this scatter, which are not correlated to the power spectrum, not correlated to the local density. And these are introduced as errors, and that explains why there are larger and larger redshift, and that is taken into account. So all our results are marginalized over a set of extra errors that we added to our likelihood. If some of those errors are not well modeled, because maybe, for instance, lensing should also part of the story. We estimated the length is subdominant. We considered that. We estimated it's subdominant, so it doesn't introduce much distortion. But of course, if we did a mistake and the length is actually 10 times bigger than we estimated, and of course that is correlated to large-scale structure, depends on large-scale structure, then this conclusion could be changed. Or maybe you should try to include that as well, to try to model the length in part. So as far as we could model, the things that we could model, we found that are not important, don't change the results. The thing that we modeled as a simple overall uncertainty due to intrinsic calibration error, intrinsic errors, they're introduced and they don't change the results. Well, they change the results include, take that into account. So sure, you're absolutely right. There are other things which are not depend on linear peculiar velocities.
Yes.
Hi. So the inclusion of a parameterization for modified gravity will enter when you go to nonlinear to the nonlinear part, and
yes,
it will improve the statistics. I don't know. I mean, I expected there will be all the complications.
Yeah, it's a very important question. So the generalization to one loop was done in essentially Newtonian physics, but now. Because people use, if you're working in this field, the kernel which are used to make this generalization are based on Einstein de Sitter. So it's not just Newtonian physics, but it's Newtonian physics in a wrong model, Einstein de Sitter, which is certainly wrong. But we generalized it. Well, people generalized it, introduced these 4 extra beyond Einstein de Sitter parameters, and all my final results, the last 2 slides, are marginalized over that as well. So in that sense, we think we are taking into account also all possible non-standard Newtonian, non-Newtonian physics by doing this generalization. Where else can modified gravity come into play is in this conservation equation between velocity, in this relation between velocity and delta. And I claim that in most modified gravity models, that correction is subdominant at sub-horizon scales, at least in all those which the extra field is supposed to play the role of dark energy. If that relation is modified, and it is modified in several cases, is modified in a way that should not be important to sub-horizon scales. Otherwise, that will not be dark energy, but will be a sort of dark matter. So I think modified gravity is into account. So I think our results could essentially be used for modified gravity up to one point, which I didn't stress. In the first part of the talk, I was using a generalized beta, which was depending also on k, on growth rate that depends also on space. In the final 2 slides, I restricted myself to the simplest case in which the growth rate does not depend on space, on k. And we know that in modified gravity, it does depend on k. It could depend on k. So we should make a further generalization, which I have not yet had time to do, but is in the same spirit, is, let's say, the next step. So we can generalize the last few results by assuming that also the growth rate depends arbitrarily on k, as we did in the first part of my talk. So not done yet. That would be, let's say, I think the most complete way of dealing with also modified gravity models.
Thanks.
Any other question or comment? Okay. What's
would you expect this method to help resolve the notorious Hubble tension problem?
So, one of the motivations was this. One of the motivations was, why don't we try to get other tensions, not just HZ, H naught, but HZ.5, HZ.9, HZ, whatever. So that was one motivation. Let's find a model-independent measure of H under the redshift and see whether this conflicts with Okay, so we started with that. So once we have data, we could produce a list of H of various redshift, and then we can see whether they agree with lambda CDM, and maybe we find further tensions. Directly on the probe of H naught, no, actually I don't see I don't see how this, because H naught is supposed to be, the local measurement of H naught is supposed to be a model-independent measure. It's supposed to be local observation, nothing to do with modification of gravity or lambda CDM. So I don't think we can do better than that.
Yeah, one other question. So you had a plot where you were showing the forecasts. I think it was for Euclid or some other mission using power spectrum and bispectrum,
Yes.
and then the two together gave a very small
Yes.
here. So I'm confused by this because if the power spectrum measurement and bispectrum were independent, at most they should go down the errors by square root of 2. So why does it look like it goes down a lot more?
Yeah, because they're not independent at all.
Okay, so
Not
but
at
how is it they're so
first things. First of all,
correlated?
this plot is misleading by eye because this is not a 2-dimensional multiplied by 2-dimensional. It's a 20-dimensional, 30-dimensional parameter matrix, some with another one, some with some prior. In this case, prior, we try to be as general as possible with priors, no priors, but there is some non-trivial prior, in particular for the show noise, but that's another story. So, and then projected. So you cannot simply say why the red is not just the product of the two Gaussian. It doesn't work that way, first of all. Second, they're not independent. All the parameters are mixed up in ways. There's also a PB direct cross correlation. That is relatively marginal. We included and we checked that it's not included in this, but we checked that doesn't make any change. But all the parameters are connected, definitely. Actually, they're the same parameters. So the level of fish, they're all together dependent of each other. And also, let me say, this is quite preliminary, so don't be confused if when we publish there is a factor of 1.5 different from this. Don't quote me on these numbers here because this is really preliminary. So we're still working on I believe we can reach order of percent, but maybe it's not 1%, maybe it's 2%. Depends on many things, as you know. So everybody knowing, doing forecast, how many things you have to assume about the survey themselves, how accurate they are. So it might easily be that we have to change by a factor of 2.
So this model agnostic approach that you call it to this
Second?
is model agnostic. You said this kind of approach in the sense that
we try to be as much as model agnostic as possible.
So you would say that this is a kind of totally empirical approach to cosmology.
Yeah, of course, with the proviso that we make several assumptions. I mentioned that at the beginning. So there are some cosmological assumptions. For instance, we believe in statistical homogeneity and isotropy and a few things, standard candles and things. So we try to be as general as possible using all the data. Yeah, maximum number is really maximum number of parameters allowed by how you bin the data. And how you bin the data is limited somehow by the fact that you don't want to introduce spurious correlations.
So parameters are significant in cosmology, at least in theoretical cosmology, as the cosmological constant. Here it would just be one more parameter in this.
Yeah, there's no cosmological constant. There's no cosmological constant at all in my set of parameters.
So okay,
that's exactly the point. There is H at every redshift, D at every redshift, F at every redshift. These are the parameters.
Okay.
Now, if you want to get from my work, what is my constraint on lambda, then either I do this and then I project on lambda, but then I will actually start with lambda CDM from the beginning. So I don't know if that's clear. So if I want to get only an information about lambda, then I'm already started with a model.
Then you need
so why should I first make a full
right.
general statement and then tell you what is omega lambda? I could do that, but so in other words, I'm trying to answer the big question with what is the expansion rate. Now, if your big question is what is omega lambda, I totally agree with you. It's an important big questions. Then it's better to redo all this in a model-dependent way.
Yeah. Okay. Even if this program would be completely successful, it would be very much successful from the empirical point of view, as I said before. But of course, we would theoretical physicists would like to understand this game from a more fundamental point of view. And then at some point, you would have to go inside the structure of these parameters, for example, H, where we would find lambda, which we would interpret as a cosmological constant, vacuum energy, dark energy, whatever, right?
Totally agree. You can do that from the beginning.
So we need both approaches because otherwise we cannot say that we have a deep understanding.
Let me say this. I would be happy if Euclid or observers or whatever at the end provide the results and things, but at the end they also say all my data can be, all the information which is in my data can be compressed into a matrix, which is not just 5 by 5 or 6 by 6, but contains these 50 or 100 parameters. And this is the result. And once I have this, I can use that to estimate any parameter, because that's just a matter of geometric projection from the big matrix to a subspace. So, or you can redo the analysis again for every single model. You can redo everything from the start. This can be seen as a preprocessing stage, or can be seen as a way to answer important questions like, is the curvature of the space 0 or not?
Okay, I'm sure that lots of questions, but it is 10 past 1. So I guess that if you have questions, you can just go and talk with the speaker at some point. Maybe he will be around here after dinner. I don't know, after lunch. Sorry.
Sure, I'll be around up to 5 or.
So in case that you are interested, you can ask him directly. But I think that we should stop here, unless there is a very urgent question. All right, so let's thank the speaker again for this nice talk.